Suppose we can start. So we have the second part of Peter's lecture on Brunn-Minkowski stability.
Yeah, very good, very good. I think most people were here last week, but let me still recall a bit what we did. We're looking at some sets, which was the sum of the elements in the sets. And we are scaling the sets by scaling all the elements. Everything we did was in Rn. A central object. From the title of the talk was the Brunn-Minkowski inequality, which says that, so this is Brunn-Minkowski, that is BM. It says that if I have two sets in Rn of the same volume, and the parameter lambda between 0 and 1, weighted average of the set has at least the size of the individual sets with, let's see, if and only if A and B are essentially the same set. By that I mean up to translation, their symmetric difference is 0, and it is convex. This is essentially convex. Or again, what does it mean essentially convex? It means if I take the convex whole, it has symmetric difference measures. All right, and we looked at the stability of this question or of this inequality, asking, okay, what if I almost have equality in this inequality? Is it true that I almost have this extremal behavior? And to that end, I presented two results, one that we dealt with last week, and the other one we'll zoom in more on this week. It's the theorem. It states that let's AB and lambda as here. Maybe notice that I dealt with the case where lambda can be close to 1 and to 0, just for my sake. Let's make this a half so that I know that lambda is always small, relatively small. Of course, that doesn't change anything, it just specifies which side I'm working on. And now, if my average is not much larger than A, so delta. And here I'm going to ask that delta is not too large, where delta is small in terms of lambda and n. Then we knew two things, okay? First being co of A minus A, and also co of B minus B. Are linearly small in this distance delta. This is measuring how far they are from being convex. And now we also want to measure how far they are from being the same convex set, which is really the extreme case.
I'm sorry, but if lambda is equal to 0,
Sorry.
Lambda is equal to 0 is an option here, right?
Okay.
And also lambda very small.
Yeah, let me say it's bounded away from 0. I mean, at 0, of course, the inequality still holds in a trivial way. But indeed, the stability, well, one of the sets is shrunk down to a point. So you can't say anything.
Well, after I was thinking, lambda is smaller than that, so you really have mostly B and slightly A, and you're comparing it to A, or is it the other way around?
So I'm always assuming A and B have the same size. So you're right that
Yeah,
this set is dominated by this term.
or B, and you're comparing it to A. That's purpose.
Well, so it doesn't really matter, right? Because A and B have the same size. So yeah.
Okay.
Also, kind of like, now there can be anything, right? Like it can be a third. So even if it's like 2/3 B, A is still contributing.
Oh, definitely. Yeah. So notice that in these bounds, we're just thinking of lambda as something potentially small, but still in a way for our purposes, we think of it as constant. Yeah. And actually, in a second, I'll switch to just taking lambda to be equal to 1/2, so we don't have to worry about it. Yeah, definitely. The lambda, you should really think of lambda in the entire range, not just when it goes to 0. All right, and what was the other result? The other result was that the convex hull of the union of the two, actually, let me write it in the same way. That this is most square root of delta over the now notice that this is a little bit too strong because everything is translation invariant. So this is up to translation. We might have to translate the two sets before this is true. The second. Okay, A plus B, the size of A plus B is not affected by moving the sets A and B around. Okay. So today I want to focus on this problem. And well, some other things as well. Now, last week, we mentioned a connection to something slightly different than this one, namely to say that, in fact, A delta B is small. Which of course is immediately implied. It's true. But then I said that actually the reverse is also true. So if we have that result and we have this result, then we also get that result. So maybe I wanted to start with a little warm up with proving that that is in fact true. And to that end, I want to prove the following theorem, which is one of the results in our paper. It seems a little bit disconnected from the other things that I'll be talking about, but I find it a very pleasant theorem in and of itself. Maybe proposition is a better word. It's saying that if I take two sets in Rn, and let's say for a second that they're convex, then I can bound the size of their joint convex hull in the following way. The size of their common convex hull normalized by the smallest of the two. For our purpose, we can always think of the two of having essentially the same size. So just think that x and y are the same size. Then this is upper bounded by the symmetric difference divided by their intercept. Okay. Very pleasant, clean statement for all convex sets. This holds true both in the range that we're interested in, which is that X and Y already look quite a lot alike. But this actually also holds true of X and Y are wildly different sets. Just looking very different. Right, so
How should I read it? Like, why are we dividing by the intersection? Oh,
right. So somehow to divide by the intersection, you want to think a bit about an example like this, where the intersection takes the smallest lengths of the boxes, and this union takes the biggest lengths of the boxes, roughly speaking. So these are the longest lengths. These are the individual lengths of the sets. This is going to be roughly the individual lengths of the sets, and this is going to be the smallest. So in that sense, it's homogeneous in that regime. That's in the regime where they look very different.
yes.
Yeah, and the regime where they're very different is one, for instance, doesn't really matter. So that's why you have this normalization. Yeah, but so in a way that regime is relatively easy side to prove. So let's focus on the regime that we're working in, which we're going to use to say that this object here is bounded by the symmetry. Okay. So let's see a proof. And we're going to prove it in a specific case. Let's say that X and Y have the same size, and they're very alike. So let's say that the symmetric difference is relatively small, is at most 0.1 times. What are we going to do in this case? So let's consider the following image. So I have these two convex sets. Maybe draw them a bit more suggestively as polytopes. So this is one of my polytopes. Let's assume they're polytopes. And my other polytope looks something like this. Now, what am I going to do? I'm going to consider the following helpful set. I'm going to consider the intersection of the two sets, so everything in this region, and I'm going to add to it the vertices of the two polytopes, which I'll denote by B of X, the vertices of X, and V of Y, the vertices of Y. Now, why is this a nice set? Well, I want to somehow leverage this linear result that I have. And I'm going to use it for this specific set. Maybe it's somewhere where you can actually read it. So now let's think about K plus K over 2. And take the average of K with itself. What do I know about this set? Well, it's made up of out of a few things. It's this intersection averaged with itself. Well, this intersection is the intersection of convex sets, so it's just convex set. Okay, a little bit boring. It's going to be the average of the vertices with themselves, again, this is, I'm assuming it's polytope, so these are finite sets. So, okay, there are some points, but there's no mass there, there's no volume there. So from my volume considerations, that's not interesting. And I'm going to say the average between this intersection and those vertices. There's something interesting is happening. So this is contained in the following things, in the intersection, okay? The average of the vertices. Boring. Now let's consider this last set. The average between the intersection and the vertices of X, union vertices of Y. What do I know about this set? Let's think of this picture. I'm going to claim that maybe let's take them one at a time. Let's take this one and the same set, but with the vertices of Y. Now notice that this object here is a subset of X, right? So this average is definitely going to be contained inside of X itself. Okay, this is contained in X. This is contained in Y. So if I consider k plus k over 2, the size of it, it's going to be completely contained in X union Y. Aha. Okay, but how big is this? It's actually not very big compared to k itself. Okay, because what is the size of k? The size of k is going to be dominated by this intersection. Of course, these things don't have any volume. So this, well, just is the size of the intersection plus the size of the symmetric difference, which if I want to normalize it to k, is 1 plus the size of the symmetric difference divided by the size of the intersection times the size of k. Okay, nothing fancy going on. But now let's recall what my linear result was saying. My linear result was saying that if I consider the distance to the convex hull of the individual sets, it's going to be linear in the growth over the.
Why did we get K in the end?
Sorry, yeah. So the size of K is just the same as the size of the intersection. Yeah. I just wanted to express it in terms of K to make it look a little bit like the inequality. So yeah, so for our purposes, this thing is going to be delta. Okay, but now what does the linear result give? It says that the size of rho of K, maybe let's say minus K. No, let's just write it like this. Size of rho of K is at most 1 plus something linear in delta. Okay, but what is this convex hull? Well, this convex hull is the convex hull of all the vertices of X union all the vertices of Y. It's just a convex hull of X.
You need convex or minus instead K, or
Sorry.
you need to subtract K from there?
Yeah, so that's why I put the 1 here.
Oh,
Yeah, let's just bring the minus k to the outside. Okay, so this co of k, it'd be nice if we could read everything. Yeah, so let's just say we know that this co of k is the same as co of x union y. And then rearranging gives something slightly stronger than that. It doesn't give the minimum here, but actually gives the intersection of two sizes. We take the minimum for the other extreme range. Yeah. So here we find that a weak version of this result shows the equivalence between the result between a symmetric difference and the common complex whole. Notice that we use something slightly weaker than here because the set that we averaged with it, we were averaging a set with itself rather than averaging two differences. So we could use some result that was already available.
you're assuming the polytope assumption is not important.
No, because you can just approximate your x and y arbitrarily well with polytopes and everything behave, like all of the properties here behave nicely. Yeah. Right. Sorry, I said we use a weaker thing, which is true for this bit of the argument. But we also want to use the linear result in a different part if we want to switch between the two. Namely, here our sets are going to be convex. So we better make sure that if we switch, we're allowed to do it also with non-convex sets. But of course, if you give me the information that x and y are not actually convex, but are very, very close to being convex, which is the information that we have, then this argument will still just hold up. Okay. So from now on, we can focus on the symmetric difference. So this we showed last week. Suffices to show the square root result for symmetric difference. Again, up to translation. Now, this reduction uses, as I said, uses a linear result. So this was not known. So a lot of the literature actually focused on this slightly weaker notion of symmetric difference. It's not actually equivalent to the stronger notion of convex. So let's see a little bit of history. For this, I'm going to consult my notebook, just to get a sense of what was known over the years. And it starts with Simonyi and Fratelli, who were focused on the 2008, who focused on the isoperimetric inequality. So they focused on the case that our A was a ball, and they were really focused on the limit as lambda goes to 0. And they showed that in that limit, if you say, let's write alpha for this thing. They showed this, essentially this behavior. It's a little bit hard to state in the lambda goes to 0 limit. You have to be a little bit careful what you mean, because we can't really let lambda appear there. But they essentially showed a square root result, a bit like that. I'm not going to say it explicitly, but morally they showed that this is the behavior that you get, the limit. Now, very quickly afterwards, having swapped out, let's go for Figazi, they showed this bound in the case that A and B are both convex sets. They show that indeed you get this behavior. Now this is still sort of, they use it as a motivated by the isoparametric inequality again. But in this case, the anisotropic isoparametric inequality. The idea being that you don't quite measure the surface area in all directions the same way, if you have a measure that depends on the direction. Okay, then in 2018, they showed again, it's going to be a repeating refrain. They showed again this result indicates that A is a ball. Again, you can see this as sort of an isoparametric inequality in the case where you don't measure the surface area by some infinitesimally small ball, but actually by a ball of some constant radius.
Now for EV.
Sorry.
The third result is now for NEV, just assuming A is a ball.
Yeah, so A is a ball, NEV. Yeah. Okay, this was pushed a little bit further by roughly in the same year. Yeah, I've got 18, and then later by Chiesi Julin. Here the order is a little bit strange. It's published earlier, but it's a weaker result. So I think not quite sure what happened there. Carl and Maggi proved the quantitatively suboptimal result, and Barchiesi and Julien then pushed it to the correct thing. Again, this metric indicates that A is convex and B is anisotropy.
Explain again how if A is the ball, how do you view it as an isoperimetric inequality?
So you mean if you don't go to the limit?
If you go to a limit, I just didn't understand.
Okay. So let's say I give you the set B, and I'm going to sum it with a tiny ball. This is set A. All right. What is A plus B going to look like? I've already taken a slightly different normalization, but so imagine this is lambda A. Then what I'm going to get is I'm just going to get the original set, but I'm going to get that my set grows a little bit around the boundary. So this new set is lambda A plus, well, in this case, plus B. 1 minus lambda B, but as lambda goes to 0, the difference is very small. So what I'm going to find is that the size of this set is going to be the size of B itself, plus this really small thickened boundary. So let's imagine that this has radius epsilon, then everywhere in this picture, I'm going to stick out by epsilon. So the size of the subset is going to be my original set plus the size of the boundary times epsilon, because I've got this epsilon times, let's say, the perimeter of B plus something in terms of epsilons, low order terms. So here my perimeter appears, and the question of what minimizes my perimeter becomes equivalent to what minimizes this subset here.
Okay, but the A delta B, I mean, where is the semantic difference between this B and this A?
Right, so what does this stability say? Yeah, again, you need to be a little bit careful with the normalization, because as my lambda goes to 0, this delta will also go to 0, in the sense that this epsilon will go to 0. But if you think about what minimizes P is what minimizes the subset. So just from an extremal perspective, if you got stability for a second, in order to minimize this subset, just by Brunn-Minkowski inequality, we need that A and B have the same shape. So that A delta B is 0, or if you think about stability, it should be small. So B better look like a ball, which is the registered isoperimetric ball. Yeah.
One question. I remember the last time you said that your result was not able to recover the stability for the isoperimetric inequality. But I'm not sure I remember correctly, but someone said that some previous result, maybe more specific for A equal to a ball or a convex set or something, was able to recover it.
Right.
But these are not those.
Yeah, so for instance, this paper is really focused on the isoperimetric problem and almost gets this as a side effect.
I understand, but Figalli Maggi-Fratelli, they are not using the Brunn-Minkowski inequality to prove the stability. The stability of the Brunn-Minkowski inequality to prove the stability of the.
Yeah, so you can't just plug this in and hope for the best.
Oh, so there is no one who's able to prove, even in a special case with A equal to a ball or something, to prove a stability for the Brunn-Minkowski that is so strong that it implies the isoperimetric inequality. I
don't think so.
Okay, thank you.
Yeah, so it's not entirely clear to me that it would be completely impossible. I know for them, it's saying that essentially the same result proves both. But you want to optimize slightly differently. So if you think about, for instance, our result, it's very poorly designed if you were out to prove something. Because for our purposes, we can't really let lambda go to 0, because then also our delta needs to go to 0. So it's a little bit hard to see what the correct control would be. Yeah, so for our purposes, you would need to get super tight control over what this bound is that you have here. Because you want this delta over lambda to stay constant. So you need this bound here to be linear in lambda. And then also our conclusion, when you look at the common convex hull, is not the right notion, because there might be points far off. So the symmetric difference is really the measure that you want to be working with. Okay. Right, so this is in this direction where you take one of the sets to be very clean in a convex set. Yeah.
Is the square root bar tight for already for all of these special cases?
Sorry.
Is the square root bar tight for all of?
Yes, yeah. Oh, I wanted to do an example. I didn't do an example. Last week we did many examples. Today I wanted to do only one example. So maybe let's do that example now. And it's exactly the example that shows that this is tight. And the way to do it is to consider a rectangle with one height 1 plus epsilon. So let's say this is A. And now I'm going to take another rectangle. Looks very similar, except that it's stretched out slightly in the other direction. So that's just B. Now, what does A plus B over 2 look like? It's going to be a square of size is going to be 1 plus epsilon over 2 squared. Yeah, it's the size. Which you might notice is 1 plus epsilon plus epsilon squared over 4. Now, of course, A and B just have size 1 plus epsilon. So really, the delta that I'm going to find is going to be of the order epsilon squared. But if you think about the symmetric difference between A and B, and delta B is going to be of the order what happens in these strips. So that's going to be 1 plus 2 epsilon. So alpha is going to be of the order epsilon. And that shows that we need a square root. This example also shows that the dependence on lambda is optimal. If you do the same computation, but with lambda not equal to 1/2, but to something else, it will get the 1 over lambda. Right. Okay, so this is in the direction of simplifying by taking one of your sets special. There's also the direction of trying to just do it for everything and get quantitatively a suboptimal bounds. So in that direction, I want to mention Gali and Garrison in a year. And that year is 2017. So they actually did work not for alpha, but for omega. So let me say that's this measure, let's say -1. So they prove a result for all A and B, but it's quantitatively suboptimal. To be precise, it's going to be delta to the lambda to the 3 to the n. Okay, that's quite a title. Yeah, yes, it's a quantitative result, but only barely.
How do you get such a result?
Sorry.
How do you get such a result?
Ooh, yeah, it's using a very wild induction, essentially. Yeah. Okay, so quantitatively, not quite there. And maybe let me mention one more result, which is my own result, yes. With Hunter Spink and Marius Tiba from, let's say, 2023. Which does show the sharp results. And let's call the lambda, but only in 2 dimensions. Now in a second, we'll see why 2 dimensions are actually nice, so it's worth mentioning. Right. Now, rather than diving into the proof of this quadratic result, I would like to mention some new results, which come out in the next week, 2 weeks, which is a connection to the functional context. Yeah. Yeah, I would like to keep all of this on the board. I'll work on here. So the basic notion is, okay, we've got this thing for subsets of Rn. What if we want to say something about functions? Let's say non-negative functions on Rn. And there is an equivalent, well, not an equivalent, well, yes, equivalent, but a similarly spirited theorem called Brascamp-Lieb's theorem, which says that if I have these functions, which are like before normalized so that the integral of f is the integral of g, and now I would like to have a notion of this sum set. So what should that notion be? I'm going to define it as a function h, which is defined as follows. Let's take the supreme. Let's say that h defined at the point z is the supremum over all x and y which average to z, and take the geometric mean between f and g. Okay. So in some sense, it's some weighted average between these functions. And then we know that the integral of h is at least the integral of f, which is also the integral of g. Okay. So this is the
Great.
there. Let's see. Okay, so let's see for a second how this relates to Brunn-Minkowski. Well, notice first that it immediately implies Brunn-Minkowski in the following way. Let's say I have A and B subsets of Rn of the same size, and I let F just be the indicator of A, G be the indicator of B, then H is going to be the indicator of their average. Okay, so that if you evaluate this integral, is just going to exactly state Brunn-Minkowski. So far, so good. So it's at least the strongest Brunn-Minkowski inequality, but now I want to say that actually the implication also works in the reverse direction. Though it's a little bit more difficult. And we really use that we know the Brunn-Minkowski inequality in all dimensions. Because of the following reason. So let's say I have these f and g on Rn. I'm going to define sets in a higher dimensional space as follows. So I'm going to say, let's take my set A, which is going to be in Rn plus k. So I'm going to add these k dimensions to my space. And what is it going to be? It's going to take a point in Rn. And at that point, I'm going to put a square of volume f of x. Now, how big is a square like that? It's going to have side length fx to the 1 over k. And then in the k dimensions, it means it's square. So, okay. Okay, let's do the same for b, blah, 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 with a g there. And now let's think about what is a plus b over 2. Well, if I want to see what this looks like at a point x in Rn, so I'm going to write this just like this object. Or maybe let me write it a bit more suggestively by writing a z here. I'm going to look at all of these cubes spread out through space, which together sum up to this position z. So of course, all of these are sums of cubes. So the object that I'm going to get here is again a sum of cubes. So it's going to be these average cubes. So my claim is that this is the supremum over all x plus y over 2 that are equal to z of f of x to the 1 over k. Y k. And then k dimension. Does it make sense? Why this would be this a plus b over 2 at point x. Okay, so now all that's left to do is to consider what is this object here? And why does it relate to this break up a line thereabout? Well, how does this object relate to that object? Just take the limit as k goes to infinity. So note fx to the 1 over k, gy to the 1 over k, over 2 to the k tends to square root of x g of y s k. Okay. Now, careful people might worry about the fact that we take this big supremum, that you have to be careful about taking order of limits and stuff like that. You're right. So to clean up this argument, you might have to do some approximation saying that maybe f is supported on some bounded region, because otherwise things get out. Morally speaking, I think this is sort of the spirit of what's going on. All right, so we got the break up a line inequality. Now, let's think a little bit about stability with this inequality. And maybe this intuition gives us a sense of what the correct notion should be if we're talking about stability. Or even just the extremal cases. What does the extremal object in this inequality look like? And because we're using this Brunn-Minkowski bound here, in order to get equality, we better get equality, or at least something that tends to equality in the Brunn-Minkowski inequality. Which means that these objects A and B better be convex in some sense. It's a bit hand wavy. let's make it precise. By considering the notion of a log-concave function. Something that I've been hearing so much about in the special year, but always in ways that seem to be completely detached from anything that I think about when dealing with log-concave functions. So, yeah. Let's just define a log-concave function. Log-concave function is essentially a function that locally obtains equality, as inequality in this supreme. So a non-negative function L, let me say L is log-concave. If all x and y in Rn and a lambda between 0 and 1, I have that L evaluated at the average between 2 points x and y. L is at least geometric average between the two.
Log of L is concave.
Sorry?
If log of L is concave.
Indeed, if log of L is concave.
L is supposed to be log.
Sorry.
Never mind.
So that's the inequality, this equality case that we get here. With equality, if f is essentially the same as g, is log-concave. So compare that with the statement here. It's roughly saying the same thing, but in a slightly different way.
How is log-concave the same as convex? Can you spell it out a little bit?
You said
Sorry,
indicator
I
function
mean,
of a
if the
convex.
indicator function of a convex is supposed to be log-concave, is that true?
The indicator function of a convex set is log-concave. Yes.
Okay.
Yes. People have tried stability of Brascamp-Lieb. Many years, unsuccessfully, essentially. So well, I've removed it now, but many things were known for Brunn-Minkowski. Right? Special cases, maybe simpler cases, like okay, we could do it in 2 dimensions. If the two sets are convex, maybe one of the two is convex. For Brascamp-Lieb, even if the two functions are log-concave, which is the equivalent of the set being convex, suboptimal results. Even in 1 dimension, best result is done.
If you're able to prove it in 1 dimension, can you obtain it in any dimension immediately?
Sorry, good.
If you're able to prove it, so if you're able to prove the stability of a linear in 1 dimension, can you immediately obtain it in any dimension as in the proof? Do you see my point?
I do. So you don't quite get everything in one go. But it is true that it's a bit more amenable to bootstrapping than the Brunn-Minkowski is. Yeah. So only very recently, and sort of in parallel what we did. The one-dimensional both functions log-concave case was managed quite fast. Yeah, so let me state the the only result that was obtained in general, which is by let's see. Ramos in 2023 is again moved even up, a qualitative bound of the same form that we saw before. So something of the form delta to the lambda to the 3 to the n. So somehow that bound came back. Okay, but I haven't stated what the actual stability results look like.
But in their proof, do they use the stability for the Brunn-Minkowski, or it's just the same bound? The same methods?
I think they mostly just follow the same path, and they need to tweak it here and there. But
Because again, in one dimension, Brunn-Minkowski implies this is in one dimension for log-concave, right?
no. This is for all F and G.
Okay, sorry. Okay.
Thank you. Okay, but let me first state what they should look like, and then it's a little bit easier to state what they do look like. Because there is a significant difference between the setup for Brunn-Minkowski and this Brascamp-Lieb regime, which is that we can't really take the convex form or the log-concave, if you will. And why is that? Well, I think in the Brunn-Minkowski world, what we saw is that there was this example where you take let's say a cube, and you take some point, and you let it run off to infinity. You couldn't really deal with that. But in that case, the doubling was at least, delta was at least t to the n. So we could exclude this case by just assuming that delta was okay. Now imagine a similar setup in the functional world, where let's say we have that f is an indicator function on some region A, all very well behaved. But now f is also non-zero at some point, very far away. And now to be a little bit annoying, let's say that f is delta to the 100 on some point very far away, some indicator function on some point very far. If I think about my h, it's going to register this in the sense that just like with that point that I noticed before, I'm going to get this region here somewhere where the function is greater than 0. But because now I can choose my function to be very small in here, I can make sure that this region doesn't really contribute. So the integral of h is still small. Okay, this was something I couldn't do before. Problematically though, if I take the smallest log-concave function bigger than f everywhere, as this point tends to infinity, that function does actually grow. So I can't take this notion of log-concave whole, or just the equivalent of this notion of a convex. So the correct notion should be something slightly different. And in a way, it's more akin to our symmetric difference. So let's say next week. FGH as before, with the property that the integral of h is at most 1 plus delta times the integral of f. Then there exists a function L, non-negative function L, which is log-concave, which has small symmetric difference to Q. Which might feel a bit in between the statement here and the statement there. So the equivalent of this statement would be to additionally demand that L was always bigger than F and always bigger than G. That's sort of the equivalent of containment in this world. But that statement by this example is actually not true. So in a way, this is the strongest argument. Right. Okay. I want to take a break, almost. I want to push a little bit further, because this is pretty for line there. But there's actually another inequality. Which, okay, in this world, by the proof that I gave of this inequality, this might seem like a natural condition. The square root seems like what happens when I push my Brunn-Minkowski bound to the limit. I get the square root bound. But it turns out that you don't actually need this square root bound for this conclusion. You can actually put a weaker lower bound on h. So rather than taking the supremum of the square root, I can replace this square root bound by the following bound. Let's take f of x to the power p, g of y to the power p over 2 to the power 1 over p. As long as I demand that p is at least minus 1 over n. So this feels a little bit like a Brunn-Minkowski bound, but now the powers are actually negative. So where the Brunn-Minkowski was approaching this from above, was in a way doing this with p greater than 0, but p tending to 0. I'm now saying actually I can push and not stop at 0. I can actually push a little bit further, as long as I don't push further than minus 1 over. And then the conclusion is still true. And this new bound is called the Brascamp-Lieb. So it's really pushing this object to the limit. And again, you can ask, what does the extremal object look like? And in a way, it will be similar to this log-concave, something that I will call p-concave. And where here we said log of L is concave, here we're going to say L to the power p is here comes a little catch, is convex if p is smaller than 0, and concave p is greater than 0. Okay. Seems like this seems more difficult than really what is going on. It's essentially just saying I want a function for which if I compute this h of z for f is equal to g, my H is just the same as my F was. So it's just saying I always obey inequalities of this type. So let me call it P-concave. And then how it works out, there's just something is turned on its head. If P is negative, you're dividing by the value of the function. That's why it becomes convex. And so, okay. So that's the, for P bounded away from -1/n, those are the extremal functions, these P-concave functions. Then if you really want to push it to the very limit, so if you actually take P to be equal to -1/n, things get more difficult and your extremal class becomes richer. Yeah, but I don't want to get, so there's a paper that whose only focus is to characterize the equality cases for P is equal to -1/n. It goes a bit too far. Okay, let's take a 5-minute break and then we'll get into some proofs. So we saw that this Brascamp-Lieb is a slight strengthening of the Brunn-Minkowski inequality. And we do also get stability for Brascamp-Lieb. So we do also get the same result with P-concave functions as long as we're bounded away from this very minimum. So we do require P to be strictly bigger than -1. So with this on the board, let me mention if something was known in the Brascamp-Lieb world. So what was known in the Brascamp-Lieb world, essentially this with the bound that I just showed, delta to the lambda to the 3 to the n. And in the very specific case that f and g are both log-concave functions over R, so in one dimension, then also the sharp boundaries. Brascamp-Lieb, some papers work for P is greater than 0, which in a way is weaker than the Brascamp-Lieb inequality, but nothing below 0. Not even a qualitative result.
But the rigidity cases were already known.
Sorry?
But the equality cases were known.
The equality cases were known. Yeah. So maybe one thing to point out is that there was some work here to figure out what the translation was that you have to use. This is saying up to translation, these sets look like the same convex set, but what translation should you use? Okay, not super clear. But then once you know the translation, you do know the convex set because it's just the convex whole of these two sets. So in a way, there's an added difficulty here because on the one hand, sorry, I should have noted that. This is again up to translation. So to prove this theorem, there's one thing that you have to do is you have to translate the functions to look like each other. But then you can't just take the log-concave as we saw before. So you have to do some work to figure out what is this log-concave function that they look like. And in a way, that's a very non-trivial part of this difficulty. Yeah. Now, akin to the result that I mentioned before for the Brunn-Minkowski, our proof of this result falls into two parts. One part, the same parts actually that we saw before, namely proving a linear result and proving a quadratic symmetric difference result. So one part is to show that f minus g scales like root delta. Again, up to translation. And then the other result is it's a little bit different than this linear result that I mentioned here. It's a result that says, in the special case that f and g are the same function, if f is g, then there exists a L, which is p concave, so that L and F look a lot like each other. In this case, it's going to be that they look linearly much like each other. Okay, so this is equivalent not to the statement that was written there, but for the statement where a and b are the same function, which was known already. And now notice that by the argument that I gave at the very beginning, this reduction from this result to the combination of the other two results, we can do the same, morally the same argument for these functions to reduce to the combination of these two results. So again, translate, take the intersection, which in this case is take the minimum of the two pointwise. That function will have small doubling and will thus be close to in symmetric difference distance to a p concave function, which will then be close to the individual functions that we started with. So there's these two parts. Two parts to the proof. Now let's do some proofs. And for my proofs, I mostly want to focus on that symmetric difference just for sets. But as it turns out, some of the arguments will also be used in the functional setting.
Just one question. Yeah. In the functional setting, you are like even in your proof, you're not actually using the stability of Brunn-Minkowski. You are reproving everything.
No, we're definitely using it.
Oh, you are using it.
Yes.
Is it an argument on the level sets of the function f? So?
Yeah. So maybe actually that's a fun thing to go. So we do both. We use the techniques that we developed for Brunn-Minkowski, as well as just black boxing Brunn-Minkowski. So maybe let's start with giving a proof of this Brascamp-Lieb inequality, because the proof that we gave for breakable angle, of course, doesn't work, right? Because we really pushed it to the limit there. So let's see why we can still use the Brunn-Minkowski inequality to prove this Brascamp-Lieb. Exactly using the level sets that Federico mentioned. Okay. So to that end, consider my functions f and g. I'm going to talk about my level sets. Let's see, notation shall I use? Let's say ft is going to be those points in Rn for which f of x is at least t. Capital G of t is same for g, and h of t for h. Now let's translate this condition here to some condition for these levels.
Also, I mean, to me, I don't understand what it means for p to be at 0 and minus 1 over n. Sorry, I just don't have intuition for these things at all.
No, neither did I. So for me, I wasn't really, okay. I've stated here in a way that I like stating things, namely with the conclusion being very clean. I think traditionally both Brunn-Minkowski and Brascamp-Lieb are stated in horrible non-homogeneous ways, which make it very hard to get what is going on. Yeah, but so maybe to give a little bit of intuition about why this p to the -1/n should be the why that is a reasonable thing. It's really because the Brunn-Minkowski inequality has a power 1/n. So this -1/n is really going to compensate. It's going to catch that 1/n that you get from the Brunn-Minkowski inequality.
It has a power 1/n.
So in the Brunn-Minkowski inequality, if you don't state it so nicely homogeneously, it says that a plus b to the 1/n is at least a to the 1/n plus b to the 1/n.
Root of n is like the radius.
Or if you want to just a little bit more like an average.
What's the radius?
Volume to the power 1, and I don't know. It's like
the radius
think
of
of
the
it as
set
like a
or something?
radius of a ball of the same volume, right?
Yeah, so where does 1/n come from? Just think of cubes
Okay.
of, then this is the side length of the, this is the side length of the cube, side length of the cube, this is going to be the average of the side lengths of the cubes, okay. So now, to see where it came from in that previous world, let's think of f as, let's say just the indicator function on a unit cube. Okay, it's very clean. And let's think of G as a rescaled indicator on a rescaled set. So I'm going to say, maybe that's not usually 11. Let's say it's epsilon n times the indicator on a square of side length 1/epsilon. Okay. Now, what is this h going to be? Well, okay, these are both scaled versions of indicator function of cube, so it's going to be some cube and some scaling. Okay. Okay, if you just think about the support, this support is a cube, this support is a cube, and the support of h is going to be the average of the supports. So, in this case, if we think about this formula, we're going to find that h is going to be the average of the functional values. And where is it going to be that? It's going to be that on the average of the two cubes. 1 plus. Right. So now let's think about this p. What values of p can we take so that this thing still has integral 1? Well, how big is this cube? Well, that is 1 plus 1/epsilon over 2 to the n. So this is the integral of h. Is going to be this times this. So now what is the limit you can push this p to? The smallest p for which this is still greater than 1 is exactly -1/n. Because if p is -1/n, then what do we get here? Well, this 1 to the p's, of course, just 1. This is going to be 1/epsilon 2, and this is going to be -n. And these two cancel. So the contraction you get in the support should be compensated by some, or yeah, contraction, growth, whatever, however you want to see it, should be compensated in the functional value. Right. Level 6, yes. Maybe let me introduce a little bit of notation. Because this is a bit of a pain to carry around. So let me have the following notation. If I want to denote that average, I'm just going to denote the p mean of A and B is going to be A to the P plus B to the P over 2 to the 1 over. So how do these level sets reflect this property that h of z is at least m of p of x, f of x and g of y? I want to claim the following. If I think about h of m of p of two values s and t, this is going to contain f of t, p of s over 2. This is a horribly a lot of notation. But this is really, there's really nothing going on. There's genuinely just a translation of that property. Right? It's just saying that if for some f of x I know is at least s, no, I said the order of the alphabet. This is at least s, and g of y is at least t, then exactly by my condition, h of x plus y over 2 is at least mp of x, mp of f of x and g of y is at least the average of s and t. Nothing fancy going on. So not only is this a conclusion, if we have this for all s and t, these two are actually equivalent. This is really just a different way of looking at it, whether you look at it through horizontal slices or through vertical fibers. Okay. So now let's see not only how Brunn-Minkowski comes in, but also how this notion of optimal transport, which seems to be a very hip method in this area, how that plays nicely with those levels. By doing the following. Maybe let's notice one more thing about these level sets, is that they really capture all the values. In the sense that if I think about the integral of the sizes of the level sets, is the same as the integral of f. There are names for statements like this that people know. So I want to capture some of that behavior. Using a transfer map, yes. It's a very simple transport map that's going to push the non-negative numbers into the non-negative numbers in some nice controlled way. Namely, it's going to have the following property. Let me write it in two ways. I can define it by differential equation, because the derivative of p is the size of ft over, I should not be using t when I speak because that It's going to lead to too many confusions. Derivative of t at s is the size of f of s over the size of g t of s. This is a local way to think about this transport map, but it may be easier way is thinking that if I take the integral from 0 up to t of the size of f of s, this is the same as the integral from 0 to t of t of the size of the level sets of g. Okay, so if I think about these functions as giving a distribution over the sizes of the level sets, it's pushing this one distribution for f into the distribution of g. All right. Okay, so now we're going to combine that transport map with that containment that we've got there and see what it gives. I think it might be time to let go of all the precious results. And maybe let me make a broader point. When it comes to these subset inequalities, these functional inequalities, a lot of the work that you need to do in order to give a lower bound, for instance, to a plus b over 2, is to find a good subset of this sum, which usually means finding which point in A you should sum with which points in B. And there's many different ways to do that. But one of them is maps like this, where you say, I identify which points in a certain level I must sum with which points in another level in order to get a good subset of this set. So let's consider that in this case. Size of H is the size of the level sets of H. Specify this. Okay. Now I can use this average here and the transport mode there in order to give a lower bound on these level sets. So this is at least H of the average of S and T of S. But then I have to adjust the way I'm integrating. S T of S. It's just a change of variables. And now I can use my lower bound. The fact that I have some subset of this. To say that I know that this contains f of s plus g t of s over 2. D I know something about this because I know the Brunn-Minkowski. So I can give a lower bound to this average here. Now, unfortunately, this is where my nice homogeneous formulation breaks down because I don't know that these two have the same size. That's a bit unfortunate, but okay. Let's try and get through that. So what is this? This is the size of fs to the 1 over n plus the size of g of t of s to the 1 over n over 2 to the power n. The lower bound. All right. And this might be the point where we start to think a little bit about what is this horrible expression there. And this comes back to what is the p average? Now, for any proper mathematician, maybe I don't count myself to per se, this is just a matter of computing things. So let's consider the derivative of this thing. P as TS. And if you do, you can see that this is in fact 1 over minus p of 1 over t prime of s. Not obvious, but true. Yeah, I mean, it's just a matter of writing it out and being very careful about your approximation. Okay, so if we were to plug that in here, what does that give? Given the fact that I've reached the end of the board, maybe I want to do 2 steps in one go. No, let's not do that. Let's keep it to 2. Yeah, let's keep it to 1 step and not that step yet. Let's express this also in terms of this t prime. So here I'm going to get something in terms of t prime. This might look like it has nothing to do with t prime, except that if we remember what t prime was defined as, it actually says something about this fs and gt of s. So I can redesign this average here to pull out f of s. Okay, so this is the size of f of s times 1 plus g of t of s over the size f of s to the 1 over n over 2 times d p times t. All right, this is nothing fancy going on, just putting out the f of s. But now this looks a lot like that object there. So in fact, now we know that this, which is it out here, this is 1 over t prime of s. Let's say 2 to the 1 over 2 to the 1 over n. Right, now, here we have another board. All right, so plugging all of this in, what do we get? We get f of s, clean term, I like that. 1 plus 1 over t prime s to the 1 over n over 2 to the n divided by term there. Minus p 1 over t prime s ds. Right, now something might be dawning that indeed what is this object? Okay, we found it through the Brunn-Minkowski application, but now we've gotten down to the point where it maybe starts to remind us a lot of what this MP mission. Here, yeah, I have it here. This thing at the bottom is really just, sorry, this thing at the top is really m 1 over n of 1 and 1 over t prime s. And at the bottom, I have m minus p to the 1 over t prime s. Now, if you inspect this a little bit, you'll see that this is increasing in P. Non-decreasing, I guess. If A and B are the same, it's always just that number, but if they're different, it's increasing in this. Which means that because P was bigger than -1/n, minus P is less than 1/n. So this ratio is at least 1. So we have that this is at least the integral of BFSs, which of course is just the integral.
This proof known, or is this part of your work?
I don't know if it's known. I suspect it is. I don't know.
I mean, the inequality is known. I don't know if this is the standard proof though. Like, I don't know the proof of the
I
inequality.
also don't know what the standard proof of this. Alright. So I was writing the Principal-Langler proof and realized I could push it a bit more, and then realized that it was known that you could push it a bit more. So it was more that I stumbled on that fact more than I was trying to prove that fact. Yeah. All right. But I would assume it is known, because these techniques are fairly standard. All right. So this crucially uses, yeah, in a way, the only real input into this proof is the Brunn-Minkowski inequality in this step. But this proof, of course, also gives a lot of stability. It is quite a robust proof, in the sense that any stability result for Brunn-Minkowski will give us some control over the functions f and g. So for instance, when I write this step, I could do a little bit better if I use stability of the Brunn-Minkowski to say, well, actually you have a little bit more, because you have something in terms of co of f of t minus f of t, and co of g of, is it s? Yes, it's s. It's co of t of g of t of s minus g t of s. So you get these extra terms that give you a little bit of boost over the Brunn-Minkowski bound, because that is what stability of Brunn-Minkowski is. It's saying, look, you get a little bit of boost over the Brunn-Minkowski bound in case your sets are not convex and not the same. So I also get some similar statement to this if some translate of fs and t of s don't actually look the same. So using this, you can already clean up your function a lot, in the sense that very, very little mass can be in level sets which are not convex, or which are not very close to. Another thing is that if t prime of s is not very close to 1, this ratio is actually a lot bigger than 1. Okay, so the fact that there's a difference between 1/n and minus p also means that if these two arguments are not the same, there is a difference in this ratio is bounded away from 1. So this proof, even though it doesn't give you everything, like that, it does help you to do some initial cleanup of your function, which is very valuable, because as I pointed out before, finding, for instance, the right notion of this log-concave function that our functions look like, or p-concave function in general, is a non-trivial task. So this sort of helps you exclude bits of f and g which behave very weird, because let's say the level sets are not convex, or they don't look alike. So being able to dispel all of this horrible looking bits of f is very valuable to doing your analysis later on. I'm glad I could show this. It leaves little time. Other things. Okay, there's one concept that I still really would like to convey, which is because this is all very Brascamp-Lieb focused. But I do think that the Brunn-Minkowski stability has some very pleasant ingredients that you would like as well.
Peter, would it be possible to at least, or just say what the construction of the log-concave function is, or no? Is that not easy to even say?
It's a result of an optimization problem. It's essentially take your f and g and keep removing bits from your functions which disproportionately let your doubling grow. So if I can remove some bit of my f and g so that delta goes down more than you would expect, do it. Okay, until you're left with some set which in some sense is locally optimal. And then take the log-concave whole of that object.
Okay, can you define the log-concave whole? Maybe it's that's all I.
Oh, yeah. So the log-concave whole is just saying, take the minimal L log-concave or p-concave, whatever the context is that you're working in, so that L is at least F everywhere. So this is the log-concave of F.
I guess, does it have a local definition as well? Like it seems like this is, you could maybe be concerned that like a log-concave, you know, the whole function being log-concave is some complicated global property, and then you have to check all of them, and then.
But it's a bit the same with a convex hull, right? Like
That's what I'm asking.
your convex hull, you can't really define your convex hull locally because you do need to notice your points very far away.
Oh, that's not what I meant by local, but like as in, right, so. But what I said is not true for convex hulls either, but I'm saying you could take like, it's something like the span, right? You're saying that, you know, this point has a small certificate that it should be in the convex hull. Like, what would that be? It would be like a convex combination of a few other points. Anyway, don't worry about it. I think it doesn't make sense either way.
So every point in the convex hull is in the convex hull of.
So something with a positive, something that is local in the sense that I was saying is the definition of like A/2 plus A/2. Like every point that's in that has, you know, you can show why it's in that with just 2 points that are in A.
Yeah, so for convex sets, you can do this with n+1 sets, and the same for these log-concave also.
Oh, okay.
I guess it's also n+1.
Well, then that is what I was.
Yeah. So you can, in that sense, it's
okay.
But local, I mean, these points can be very far away, right? Like if I want to prove that this point is in my convex hull, I need to register both this point and those points.
Yeah, by local, I mean it like you have to test a small number of memberships in A or something.
No,
There's
no, that's still true there.
So going back to what you said, there was a counterexample in one of the boards on this side that showed why a log-concave hull is not going to be good because it's very far from the symmetric difference is not small.
Yes.
So in your optimization problem,
You need to make sure that those points far away, because the point that I drew, even though it has zero mass, because it was just a point,
Mass on
it
this.
made the doubling very big. So removing it was very cheap from the perspective of removing points because there was no mass, but it was very useful in the sense that it brought delta down a lot.
So that's kind of what you're doing.
That's sort of what
optimization.
you keep doing. Yeah. And that is good enough, apparently, because it gives you the correct set, the correct function. All right. Okay. Incorrect proof of the stability of Brunn-Minkowski. Let's assume for a second that A is a finite union of cubes. It's not a cube. And B is this one. Now, one proof of the Brunn-Minkowski inequality is by induction. It's saying I can find a hyperplane, find a corresponding hyperplane for the other set, which leaves the same amount of mass on both sides. If I can prove it on both sides, I can prove it in total. And at the end of my process, I'm going to be left, if I started with a finite union of cubes, this process, I can use induction to say, I'll be left with just summing cubes. And for, or not cubes, but boxes. And for boxes, parallel axis aligned boxes, very easy to prove. Brunn-Minkowski. Okay. Nice simple proof of Brunn-Minkowski inequality. Now I can say, run this process. It's also very easy to prove stability for the Brunn-Minkowski inequality if you're just left with boxes. So I know that, let's say, A0, A1, A2, B0, B1, B2. I know that at the end of this process, because of the stability for each of the boxes, let's say I denote delta I for the doubling in one of the regions. So delta I is AI plus BI over 2 divided by AI minus 1.
Are we assuming that AI has the same mass as BI?
So you did?
Are we assuming that AI has the same mass as BI?
Yeah, exactly. That's the crucial. So we cut with these planes to guarantee exactly that. The size of AI is the size of B. So we define these sort of local doubling in each of the regions. And now by the fact that I know in each of these regions, my boxes are well behaved, so I know the symmetric difference is small. So I find that the symmetric difference between AI and BI is at most square root delta I times AI. Yeah, very nice. Let's take the sum. The sum of the symmetric differences is just symmetric difference. And by convexity, concavity, whatever the right notion is, this is actually smaller than square root delta times delta A. QED. Okay, why is this not correct? Why is this not a correct proof? Seems very easy, very quick. Could have done that.
Symmetric differences can be large and some small.
Sorry?
Some symmetric differences can be large.
You mean if I take this? Well, this will always be true. So this will always be true.
Okay.
Yeah, so this is just the stability in each of these regions. Okay, if a delta I is large, then maybe I will still have this stability, but for a very silly reason, namely, if delta I is large, then maybe I should add a constant depending on n there. then it's just true for trivial reasons. In the sense that if this is bounded away from 0 by something in terms of n, by taking this constant very large, I know that this symmetric difference is at most the size of AI. So that's trivially true. So that this bit, like this statement in itself is definitely true. Well, reasonably true. But why does it not work to take just the sum of origin?
Is that exactly the last inequality, the one that brings you from square root of delta I to square root of delta?
That one's also true. That's Jensen's inequality.
I mean, these hyperplanes, were they the same when you did this split? And how do you-
Parallel.
But kind of the shift is, it's the same transformation? You do to all the pieces?
Right.
I'm asking if you do the symmetric difference between A and B, is it equal to the symmetric difference between the pieces?
Right. So yeah. So that's the catch, right? I won't actually know that the symmetric difference is small. I know that the translation, like I need to translate each of these sets. So really, there's some translation. Let's say VI here for which this inequality is true. So that this is true, but then this VI, if it's not the same for all of them, I can't find a single translation. Okay, so a lot of the work is finding what is this correct translation. And this is a very important ingredient in the Brunn-Minkowski inequality, the stability for the Brunn-Minkowski inequality. Just my last minute. I will throw one valuable word at you, which is that if I have my set A and my set B, how am I going to use a concept like this? Some concept where I'm going to cut it into smaller pieces that are easier to deal with, but still get the translation right, is going to be cones. Cut my sets with parallel cones. And now, because I know that my set is already quite convex, so let's say I may assume that there is this ball in the middle that is contained in both. If I can now prove this result in each of the regions, this translation must actually be the zero translation. So why is that? Well, if I think about this region here, and this region there, if the symmetric difference between this region and that region is small, it better be that the translations align these sides. Because if I pick out this set, what does it look like? Well, it looks like a set where all of this is contained in my set, and then maybe something happens out here. And similarly for the B, so if I were to align this set and put it down here, I also know that B contains all of this region. So if I shifted a little bit the region in B, it would immediately cause a massive symmetric difference between A and B. So if I can prove it for each of the cones, the translations must actually align, and I can put them all together to get a globally coherent small symmetric difference. Yeah, I'm afraid that's the last one.
Okay, thank you very much. Any questions? So do cones work the same way as boxes, or
Sorry?
you split it into cones as opposed to splitting into hyperplanes? Somehow the rest of the will work?
Well, so there's some difficulty, right? Because I worked with axis-aligned boxes and I was cutting with axis-aligned planes, I had very good control of the object that I'm left with at the end. Now what I'm going to do is I'm going to start with these bounded number of cones, and I'm going to refine the cones by picking hyperplanes that contain the origin, for which there exists a parallel hyperplane through this origin, so that the mass stays the same on both sides. Now I'm way more restricted. Here I could just pick any old plane that I wanted, so it was very nice. Here I'm very restricted because I need to pick these planes through the origin. So the object that you're left with in the end is not as clean as just a box. So it is a lot cleaner than the original set. But as it turns out, what happens to these cones is that they're going to be small. That's really the thing you're saying here, right? I'm going to continue until I'm so small that I'm essentially at the scale of the atoms of my set. And here I want to say, okay, I can get small, I can make them smaller and smaller and smaller, but I can't get to the scale of the atoms in all directions. So you'll find a cone that is essentially very thin on the scale of the cubes that make up your set to begin with, in all but 2 directions. And then you still need to work with those 2 directions. But what it does is, in a way, it reduces the problem to 2-dimensional version. It's not quite a normal 2-dimensional Brunn-Minkowski because you can make them very thin, but not flat. So there's still a little bit of structure in the perpendicular direction. So it's essentially reduces it to a problem in 2 dimensions with a weird measure on the plane. And then you work in that. And then there's still quite some work to do there, but morally that's where it brings you. And for functions, in a way, it works the same, getting to the scale where your function is essentially constant in the sort of narrow directions of your cone.
So this is where it has some flavor of needle decomposition.
Sorry?
This is where it has some flavor of the needle decomposition.
Right, yeah. Yeah, I must admit I don't know too much about needle decomposition, but what Alessio told me about needle decomposition, essentially where you take the limit of this process, right? So in a way you lose some of the structure. So we don't take the limit, but we just run it for a long time, so that you still have a little bit of the structure left.
More questions? Head to lunch.